Right, well, welcome to topic 3, periodicity. As with all the other PowerPoints, the first slide usually is a syllabus statement slide. So you can see on this slide that I've listed the understandings, applications and skills, and guidance requirements for this topic. The understandings are effectively the key ideas, so the key content ideas. The applications and skills are how some of these ideas, and key ideas and content are used. And the guidance here is mostly used by teachers to assist them in some indication as to how deep the topic should be covered. But it's equally useful to students. So let's begin. In this topic, you will learn about the structure of the periodic table. You will learn about the properties of the elements in the periodic table, and you'll learn to predict trends and patterns in the behavior and physical properties of these elements also based on their position in the periodic table. The first and most important thing is that you understand the structure of the periodic table. And firstly then, the columns of the periodic table, as you'd all know already, are called groups. There are 18 columns, and in previous syllabi, students only were required to label group 1 and 2, and then over on the other side of the periodic table, what we now call group 13 to 18, students were required to label this group 3 to 8. Now in your syllabus, we must use the 1 to 18 notation. And so there will be situations during the year where there will be questions that come from old exams that still use the old notation. So if you're ever confused about this, please ask your teacher for clarification. In any case, the vertical columns, which are called the groups, are numbered from 1 to 18. Now, how the elements are positioned into those groups, originally they are positioned into those groups based on similarities in their chemical properties. We now know that as a result is due to their electronic configuration. So in effect, all the elements in group 1 have one outer shell electron. Now the term that is often used for outer shell electron is valence electron. Okay, so if we ever use the term valence electron, then please remember that this actually means the outer shell electron. So elements that have one outer shell electron are put into group 1. Elements that have 2 are put into group 2, and so on, and so on, and so on. There is a little bit of a trick with this, but we'll have a look at that on the next slide when we've got a periodic table that we can refer to. Okay, the horizontal rows are called periods. And currently, there are only 7 periods in the periodic table. That's because we've discovered up to element 118. So element 118 is actually the last row, the 7th row in the last group, the 18th group. So element 119, when that's discovered, if indeed it's discovered, I'm sure it will be, then we'll need another row of the periodic table. Additionally, students need to know some of the common names of the elements. And those common names usually are associated with the groups. Now, for example, group 1 that we were discussing before, elements that have 1 electron in their outer shell, turns out that they are metallic, and that when they dissolve in water, they produce, or react with water, they produce an alkaline solution. So they're very often referred to as the alkali metals. Group 2 elements are called the alkaline earth metals. They too are. It's group 17, commonly referred to as the halogens. Group 18, usually referred to as the noble gases, but also known as the inert gases. Groups 3 to 12, so groups 3 to 12 is this block in here. Okay, so that's groups 3 to 12. They are referred to as the transition metals. And there are a couple of others that are not on this slide that students need to be familiar with, and that is the lanthanoids and the actinoids. So I might skip to the next slide so that I can illustrate where they are. Right, so firstly, let me just point out that this periodic table is a little bit old. I probably should update it on the PowerPoint. So we're actually now up to element 118, which is called unoctium. But it doesn't really matter because we're just looking at the structure of the table. So it's not that important that it be exactly up to date. So based on what we saw in our previous slide, group 1 would be this group here, group 1, right? And that is referred to as the alkali metals. So you can see here that the color code, the orange, they're the alkali metals. Group 1 are the alkali metals. But as it turns out, one of them is not a metal, hydrogen. The rest are. Group 2, that are highlighted here in red, are known as the alkaline earth metals. Anything in there called an alkaline earth metal. So once again, they're metals and they produce alkali solutions, or they react as alkalis. And that block that I drew in the previous slide was here. So that's from group 3 to group 12. Let me just write in the names of the groups, the numbers of the groups. So that would be group 2. So this is group 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. And then we've got group 13, 14, 15, 16, 17, and 18. Okay, so the one that I've highlighted in blue, though, they are the transition metals. The transition metals here. This box immediately below that I've highlighted in blue. Now, the lanthanoids and the actinoids. The lanthanoids are the row of elements that begin after lanthanum. And that's this group down here. So these are the lanthanoids. The actinoids are the elements in the row that begins with actinium. So that's these here. Now they're particularly important. These two groups are a particularly important group of elements currently. They're referred to as the rare earths. And are very precious semiconductor metals and or radioactive metals that are used extensively in modern technology. What else? So over on the far right, group 18 are the noble gases, noble or inert gases, and then group 17 are the halogens. We'll get to do some laboratory experiments and study the behavior of some of these elements a little bit later on. Now, the periodic table also, this diagram also has some additional interesting patterns that I'd like to highlight. So if we look at the position of the metals versus the non-metals, we start up here above aluminium and do a zigzag line down around aluminium and so on. This zigzag line differentiates the metals, so everything to the left of this line are metals. Everything to the right of this line are non-metals. So just simply based on the position of an element in the periodic table, you can make pretty good deduction as to whether it's going to be metallic or not. But what differentiates a metal from a non-metal is really its chemical behavior. And that behavior is on a spectrum. So those elements that are on the edge of this line that splits the metals from the non-metals are often referred to as poor metals or metalloids, because they have properties of metals but also display properties of non-metals. Or in other words, they're not really that good at being metallic because they are also non-metallic, so sometimes referred to as poor metals. In the diagram here, see the blue colouring for the symbols represents the colouring of the non-metals, and we should also include noble gases there as non-metals. So there are very few non-metals actually in the universe by comparison to the metals. There is something else I'd like to point out on this slide, and that is something that we looked at. I'll just rub all these things out. That's something that we looked at when we were discussing configuration, and that is the blocks in the periodic table. So we've got these first two groups that have one electron in their outer shell and then two electrons in their outer shell. And we know that they represent elements that are having their S subshells filled. And we've got this block over here that is 6 elements wide. 1, 2, 3, 4, 5, 6. And this is the P block. So we know that this represents elements that are filling their P subshells. In the middle, the transitions, there's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 elements in this block, and we know that this represents elements that are filling their D subshell. And so finally, down here, the rare earths, or the lanthanoids or actinoids, this is called the F block because all of these elements have their outer shell configuration as an F subshell. So based on the position that the element is in the periodic table, we can very quickly deduce its electronic configuration. So if we take potassium as an example, we can see that it's in the 4th row and in the S block, and it's the first element in that S block. So it must have a configuration of 4s1 as its outer shell configuration. All right, so if we work back, then if we go to the next row up, and we go to the next row up here, we're now in the 3p block. So then that means that potassium has filled its 3p, so it's 3p6. And if we continue across the table, we go to the S block on the 3rd row, so that's 3s. So potassium must have filled its 3s. So that's with 2, not with 3 like I just wrote. Okay, so then if we continue the pattern, we go up to the 2nd row, so it's 2p6, and then keep going, 2s2 and then 1s2. You see from the original position of potassium, we were able to deduce its electronic configuration fairly quickly, just by looking at where it is in the periodic table. Now, just be careful with that though, because we mustn't forget that we're now using the convention 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, and 18 for our group numbers. So if we are asked to work out the configuration of aluminium, and we see that it's in group 13, but the 3rd row, this and the P block, this does not mean that it's 3p13. You've got to be very careful with that. You should view these numbers as 13, but really it means 3p electrons. 14, but really it means 4p electrons. 15, 5p electrons. Group 16 is 6p electrons. Actually, my mistake. 1p, 2p, 3p, 4p electrons. Group 17 is 5p electrons, and group 18 is 6p electrons. So you see how easy it is to make a mistake? You've got to be careful to remember that group 13 actually is the first group of the P block, so it must have 1p electron. And when you've done that, once you've mastered that, then it will be easy enough to work out what the configuration of the element is. Okay, so let's just recap and see if we can answer these questions. Question 1, what increases in equal steps of 1 from left to right in the periodic table for the elements lithium to neon? A, the number of occupied energy levels. Well, no. Lithium and neon are all in energy level 2, so shell number 2. So it is not an increase in the number of energy levels. The number of neutrons in the most common isotope? No. The number of neutrons varies in an irregular way, so it is not B. The number of electrons in the atom. Lithium is element number 3. It has 3 protons and it has 3 electrons. The next element, beryllium, is element number 4. It has 4 protons and it has 4 electrons. So yes, its atomic number is increasing, but that too also means that in the atom, the number of electrons are increasing by 1. So the correct answer is C. The atomic mass is the sum of the protons and the neutrons, and because the neutron number varies in a random way, the atomic mass also will vary in a random way. So the correct answer is C. Next question. For which element are the group number and the period number the same? Well, beryllium. Beryllium is in period 2, and it's in group 2. B. Question 3. Nitrogen is found in period 2 and group 15. Now let's not forget that group 15 meant that it was the third element in the P block. The third element in the P block. So distinguish between the terms period and group. Period is the row of the periodic table, and given that this answer is only worth 1, we probably don't need to elaborate. If you're unsure that you've answered the question fully, you can add, or you could say the shell number. The group is the number of outer shell electrons. Okay, state the electron arrangement of nitrogen and explain why it's found in period 2, group 15. Right. So period 2, the electron configuration of nitrogen is 1s2, 2s2, 2p3. So why is it in period 3? It's in period 3 because there are, period 2 rather, because there are 1, 2 shells. Why is it in group 15? Group 15 meant that it was the third element, because don't forget the first is group 13, then there's group 14, then there's group 15. So it's the 1, 2, third element in the P block. So groups 13 to 18 are the P block. So it's the third element in the P block. So it's P3. And if it's P3, then that means that it's group 15. Okay. And that's it for this podcast.